Why, hello there, lovely ones. So we're going through questions that are Euclidean geometry, looking specifically at paper 2, the IEB one, November 2016, and this is question 4b. So I have a picture over here, and yes, we could read through all of this information, but before we do that, I'm going to do an activity where I write down what I see and what I don't see. The reason I do this before looking at any information over here is because then it guides my process, my thoughts. So what do I see? I see a center. It is center O. I see a tangent. What else do I see? I see radii. And I see triangle in the things. I also see an angle at center. That looks like everything for now. What I don't see is a cyclic quad, which means I also don't have angles in same segment. And let's leave it at that for now. So the reason I do that is because when I say center, I can then start thinking about the theorems like angle at center equals twice angle at circumference. I can also think with the tangent linked with the center. I can think of 90 degrees, how it meets up over there. I don't see any chords, sorry. Chords that, well, I do see chords, but they're uninteresting. Interesting. I spelled it completely wrong, but anyway. It's tangents, they're 90 degrees, radii are equal, triangles, supplementary, and angles at center equals 2 times angle at circumference. And really, I'm thinking about all of those things before I even read the information. But now that I've started jogging my memory, let's go through it. It says O is the center of the circle. Yes, there it is. A, B, and C lie on the circumference. Okay, we got that. Line DAE is a tangent to the circle. There we go, at point A. And look, we have that radius linking up. Then they tell us that A4 is 62 degrees. So let's just fill that in over there. And A2 is 25 degrees. And we'll fill it in over there. Okay, so first bit says calculate the size of angle C1. Let's start by just highlighting where C1 is. And now let's look at the picture. So we know that this is going to be 90 degrees. We also, because there's a tangent, we can think of tan chord theorem. So will that help us? Well, I don't know. We know that this over here is going to have the same value as that over there, so that'll help. We also know that we have radii, and radii are equal to each other, so it's there and there, which means we have an isosceles triangle. So let's put that in there and that over there. So there's quite a lot going on over here. We could figure out what A3 is. And then based on A3, we can figure out what C2 is, because they're going to be equal. They're base angles of an isosceles triangle. And then because we're going to know the whole size of C based on the tan chord theorem, we can then figure out what C1 is, because C1 will be the same as the whole of angle C minus the value of C2, and C2 we would have got from A3, and we got A3 from A4 because it is tangent Okay, but now the trick is to write that all down in coherent mathematical talk. I once had a maths teacher who told me that there were many different ways to get to the top of the hill. It didn't help me, it just made me feel insecure because I just wanted to know what is the right answer. Unfortunately, she is right. If you are trying to prove something, there are many, many different ways to climb to the top. And the route I'm going to take now is not necessarily the only way. But let's go with it. So, this step over here, I started by saying that A3 plus A4 is equals to 90 degrees. And how do I know that? It's because radii or radius is perpendicular to the tangent. Okay. Then I can work out what A3 is. Therefore, A3 is equals to 90 degrees minus A4, which of course, let's do that. A3 is equals to 90 degrees minus 62 degrees, and that gives me 28 degrees. So if A3 is 28 degrees, it means that C2, which is also equal to A3, which is 28 degrees, they're equal. They are equal because they are base angles of isosceles. Now, this is not the elegant way of writing that. We could say angles at base of equals radii or blah blah blah. There's so many different ways to say things, and more of them are far more elegant than this. But okay, let's carry on. So I now know that this is 28 degrees and this one over here is 28 degrees. I need to now show that I can figure out what the whole of C is. It is a side thought. So as a personal coping technique, I then leave quite a big gap and I start a new thought. And this begins with figuring out what A1 is. Now A1 is going to equal to 90 degrees minus A2. And how do we know that? We still say its radius is perpendicular to the tangent. Let's write it out nicely. Tangent. So therefore A1, my word, is equals to 90 degrees minus, we're told it's 25 degrees, so that gives us 65 degrees. Why is that useful? Because if A1 is equals to 65 degrees, we know that tan chord theorem means that C is equals to 65 degrees as well. So tan chord. Okay, returning to the picture, and we're going to do a little bit of erasing to make it easier to see. We now know that, and I'm only going to fill in the important information. We know that this was 65 degrees and this whole thing, let's just use our blue, this over here is then going to be 65 degrees. We also know that this tiny angle over there and that one over there is 28 degrees and 28 degrees. So that means if we want to figure out what C1 is, let's just use red. We're going to take the 65 degrees and subtract the 28 degrees. I hope it's easier to see. So then we say C1. Let's just write it down. Once again, I'm leaving quite a big space. C1 is equals to C minus C2. And that is, let's write out neatly, C1, and there's 65 degrees, and it's minus 28 degrees, which gives us 37 degrees in total. The first part of question 4c is actually quite interesting because, well, it's not a question we see often. It says, what single statement can be deduced from both of the following statements? This was only 1 mark question, but anyway. It says that m plus n equals d, and then m plus q also equals d. So what we can deduce is that n has the same value as q. Interesting question, but there we go. We've answered it. Okay. In the diagram below, A, B, C, D lie on the circumference of the circle. Let's talk again about what I see. I'll draw a little eye. There we go. I see a cyclic quad. I see some triangles. I see a line that's extended. So extended line, which means it could be an extended angle to the cyclic quad, or it could be to the triangles. At this point, I don't see any angles in the same segment. Nope, no angles in the same segment. So I think I'm okay for now. It says prove that angle B is equals to A1 plus C2. Here's A1 and here's C2, and there's angle B. And this is a really good example why the act of writing down what we see is important. Because at first this looks completely can't see it. But anyway, but if we start talking about a cyclic quad, we know that D1 is going to have the same value as B1 because it's an exterior angle. And if we start looking at the exterior angle of a triangle, we know that A1 plus C2 also has the same value of D1. And this is where this question over here links up nicely, because it's pointing out that they're connected. So let's write that down. Let's say that B, angle B, is equals to D1. And that's because it's exterior angle of cyclic quad, blah. And then let's state the next thing, which is A1 plus C2 is equals to D1, and I'm going to scroll over now. That is because it's exterior angle of triangle. Therefore, B is equals to A1 plus C2. And we know that because they're both equal to D. That's enough from me for now. Much love.